everyone. My name's Tracy from the Office of the Great Barrier Reef. I'm really grateful to Barbara for her time today. Just a quick couple of housekeeping things for those that have just joined us. If you could keep your microphones on mute during the presentation, there'll be plenty of time for questions at the end. And just a little suggestion, if you do think of a question as you're going along, feel free to pop it into the chat feature and we'll make sure that we come back to those questions at the end of the presentation. I'm also really keen to hear from anyone for suggestions for other presentations. So please feel free, if you know of some research that you'd like to hear from, please let us know and we can see if we can track that research down and get someone to come and present on it. Well, I'd like to welcome Barbara and thank her again. Now, Barbara is a principal research scientist and a biogeochemical modeller. Gee, I practiced it and everything and I still stuffed it up. She's with the Australian Institute of Marine Science. Barbara's going to be talking to us today about a NESP project looking at benthic light as an ecologically validated water quality indicator. Thanks so much, Barbara.
Thanks, Tracy. So I'd like to begin by acknowledging the traditional owners of the Great Barrier Reef and paying my respects to their elders, past, present and emerging, especially any who might have joined us today. And I'd like to thank everybody for making the time this afternoon to join us. It's fantastic to have so many people joining for this talk. I'd also like to acknowledge that this project has been funded by the NESP Tropical Water Quality Hub. And I'd like to thank my colleagues working on this with me, in particular, Katerina Fabricius, Lachlan McKenna, Tess Canto and Murray Logan. So, as we all know, the Great Barrier Reef thrives on light. Seagrasses and coral symbionts require light to photosynthesize and to grow. But the amount of light that reaches these benthic habitats, benthic meaning at the bottom of the water column, varies considerably between different regions of the Great Barrier Reef and at different times, especially if you have major wet season storm events. And that light passes through the water. The amount of light that actually reaches the benthic habitats depends on both the water quality in terms of how much sediments, how much phytoplankton and dissolved coloured material is in the water, and the depth. It's just taking a moment to switch slides each time, so if there's a bit more of a hesitation than usual, that's why. This slide is just to illustrate that strong variability in water quality. It's an animation produced by the Reef's marine models for a period in 2011 when we had Cyclone Yasi passing over. And as you can see, there's strong variations from near shore to offshore. There's a lot of suspended sediments being resuspended off the bottom of the water during this time. But in addition to the brown sediments that you can see a plume of dark coloured fresh water coming out of the Fitzroy River and some greener material, which is the phytoplankton starting to respond to the extra nutrients that come with that floodwater. Every year, the Office of the Great Barrier Reef and the Great Barrier Reef Marine Park Authority put out a report card so that we can keep track of how we're doing in managing the Great Barrier Reef and how conditions are varying from year to year. At the moment, the report card has only fairly limited information about water quality going into it. And that's in part because it's difficult to relate some of the things that we routinely measure in terms of water quality through the marine monitoring program directly to the expected ecological outcomes. And it's in part because we need measures that we can estimate easily over the whole Great Barrier Reef, which is more difficult to do with some of the water quality measures that require sampling and point observation. But currently, the water quality component of the report cards has two metrics going into it, one of which is chlorophyll A and the other is Secchi depth. And both of these we know are very important. Secchi depth is an indicator of water clarity and how much light is getting through, but it doesn't directly tell you what conditions corals and seagrasses are experiencing where they are, because that's a function not only of water clarity but also depth. And it doesn't tell you how they're likely to respond to those variations in water clarity. So in this project, we're looking for a metric which can take those things into account and complement the existing measures. So our goal is to develop a new water quality index that can be applied on the scale of the whole Great Barrier Reef, that relates directly to ecological outcomes, and that considers, in this case, the chronic effects of light stress. Acute effects can also be very important, particularly for dredging applications, but in this case, we're looking at the chronic effects and the year-to-year variations. So to achieve this, we had 3 steps that we needed to go through in the present project and the preceding one, which was led by Katerina Fabricius. First step was to determine light responses and thresholds for key coral and seagrass species. Step 2 was to develop a remote sensing algorithm so that we could estimate benthic light, that is the light getting to the bottom of the water column to these benthic habitats across the whole Great Barrier Reef. And the third step was to combine these to produce a water quality index that can create a letter grade that could go into the annual report cards. So, first step, looking at how corals and seagrasses actually respond to variations in light. Okay, so there's a couple of papers that have come out of this project from work that Katerina Fabricius and her team have conducted in the National Sea Simulator, or CSIM, which is my virtual background here. I'm actually working from home in Canberra for the duration of the lockdown, but CSIM is a nice alternative background. So this slide just shows one of the experiments that was conducted looking at 2 species of coral, Pachyceres speciosa and Acropora millipora. There's images of those coral species to the right in case, like me, you're not particularly familiar with the taxonomy. And these experiments looked at coral production. They also looked at growth rate in terms of chlorophyll accumulation, biomass accumulation, and photosynthesis rates as a function of light under several different light conditions. They looked at high, low, and intermediate light, daily light doses, with either constant light or light that varied over the course of the day. And out of these experiments, there came a couple of findings, one of which was that the variability within a day in the amount of light didn't matter that much. What was important was the daily light dose integrated over the course of the whole day. And the second was that there was a light dose above which increasing light didn't really improve the growth rates of either coral species. It was fairly consistent between species, but below that threshold there's quite a dramatic response. This is just a slide showing another experiment which has been submitted to a journal and is being reviewed currently. Again showing a similar response, looking at both adults and juveniles in the full paper, and again showing that variable or constant daily light didn't really make a difference. It was the total light dose each day that affected growth rates. Tracy, it looks like there's a couple more people in the waiting room. Anyway,
Apologies,
so
I've just grabbed them. It hasn't come up on my screen.
oh, okay.
Usually I get a flashing message. My apologies.
I can. I think I've just gone in to admit them. So
yeah, I've just let them in.
Okay, thanks.
Thank you for picking that up.
So in addition to this CSIM experiment, or the series of experiments, our colleague Catherine Collier, who's a seagrass expert, reviewed the literature on seagrasses for us to find out how seagrasses respond and pull out some information about seagrass light thresholds. And of course, different species of seagrass have quite different tolerances for some degree of shading. And in general, you know, both seagrasses and corals can thrive at daily lights down to 3 to 6 moles of photons per square metre per day. But as a general rule of thumb across all of them, we found that looking at a threshold of around 14 moles of photons per square metre per day, not as the minimum light dose that they could survive and thrive in, but as the maximum that they could reasonably use to enhance growth, would be a pretty good overall threshold if we want a single water quality index. So step 2 was to develop a remote sensing algorithm to estimate benthic photosynthetically active radiation across the whole of the Great Barrier Reef. Now this is where Lachlan McKenna and our PhD student Tess Canto focused most of their work. Ocean colour satellites such as the MODIS satellite pass over the Great Barrier Reef daily and detect backscattering at a number of wavelengths. And this provides the information that we can use to estimate how light is attenuated at each wavelength. If we combine that with information about the depth of the Great Barrier Reef, so a bathymetric map, then we can use that to estimate how light attenuates across the whole photosynthetically active radiation band and how its colour and character varies with depth. And so we can use that to estimate the amount of photosynthetically active light at any given depth. We can then, even though we only have a MODIS snapshot at a particular time of day, because we know how the sun moves over the course of the day and how the angle of the sun changes, if we assume fairly consistent cloud conditions during each day, we can extrapolate to estimate the daily integrated light dose for each day of the year in each 1 kilometre pixel that we get from the MODIS satellite across the whole Great Barrier Reef and out into the Coral Sea. We've validated this against in situ light logger data at 4 sites, mostly in the mid-shelf and offshore region, but we've also done a few comparisons in near-shore seagrass sites. And especially for those mid-shelf sites, we get a pretty good matchup. So we can use this to generate a map of the benthic light dose across the whole Great Barrier Reef on each day. And this little animation here is just showing the daily average benthic light dose from each year from 2002 to 2017. Just zoomed in on a particular area where you can see there's considerable variability in the conditions experienced from one year to the next. So finally, now we have the means to estimate benthic light, or BPAR, across the whole Great Barrier Reef every day. And we have some information about how corals and seagrasses actually respond to different light conditions. So the final task is to combine these to produce a water quality index. To produce that index, first we take these daily integrated benthic light maps. Then we calculate the chronic light stress experienced on each, or the light stress experienced due to low light on each day. Now, this light stress metric doesn't consider potential stress due to excessively high light, which could exacerbate bleaching during heatwave events. It's only looking at the light stress due to low light. So given that threshold value that I mentioned earlier of 14 moles of photons per square metre per day, we ignore any additional light dose above that because they won't be able to use it for additional photosynthesis, or at least not additional biomass growth. And we calculate a daily light stress simply as 14 minus the estimated daily light dose measured in each pixel on each day. But we don't want to penalise offshore sites which are really deep and so would never experience really high light, but might still be good habitat for coral and seagrasses. And nor do we want to penalise sites that might be right in the mouth of a major river and would never experience in natural circumstances really high light for that reason. So instead of just taking the raw daily light stress for each pixel, we calculate a relative daily light stress, which is I've said max there, that's incorrect. It should be the minimum of that threshold of 14 moles of photons per square metre per day, and the 95th percentile of the light, which was actually observed in that pixel over the entire period of record from June 2002. So the relative daily light stress is the difference between that value and the actual daily light dose. You can think of this as the number of photons of light that squid cell and the corals and seagrasses in that cell are missing out on because of poor water quality. If they're missing out on light because of depth, that's not penalising the index, but if they're missing out on it because of poor water quality, then that's what we're measuring. And so to get an annual or seasonal light stress, we simply integrate the relative daily light stress in each pixel over the period that we're interested in. So this is a fairly simple calculation, but conceptually a bit complicated. So I anticipate there might be questions on that. I'll just leave that up for a few more seconds to give you time to read it. So this gives us a map for each year when we calculate the annual integrated light stress. When we do the seasonal results, we get very similar results. I can show you that later if you're interested in it. The wet season contributes a great deal to the annual light stress, both because light would normally be higher in the wet season and because there's more variability in water quality due to summer rain. But you can see that if we take a wet year like 2011, when we had those major cyclone events, and a dry year like 2016, we can see quite a considerable difference in the total light stress, both inshore, these red areas along here, compared with the green areas in 2016. But even offshore, we can see that there is quite a measurable difference in water quality and hence in the amount of light that those benthic habitats are receiving. And we can zoom in to each NRM region. Here I'm showing the offshore dry tropics, and again see how that varies from one year to the next. So we're nearly there in terms of the water quality index. Having calculated for each pixel the total annual relative light stress, we take the spatial sum over each management region and then scale that value for each region to provide a value between 0 and 1. 0 would be the worst case it would be possible to have given the number of pixels in the region and their depth. And 1 is no light stress at all. And from that value between 0 and 1, we can assign letter grades, which can be used in a report card context. And this is what we get when we do that. So within each of these panels, we have a time series from 2003 through to 2019. As we move from top to bottom, we have the gradient from north to south, and we can see that we generally have more consistently good scores in the Cape York region than in the regions further south, which are influenced by major rivers such as the Fitzroy and Burdekin. As we move from left to right, we see the gradient from the enclosed coastal region to the offshore region. Generally, offshore, we get more consistent and good scores, whereas in the coastal region, we get much more year-to-year variability due to flood events. And that's just the whole set again. We can zoom in on and think about what's happening in particular years. So in 2008, for instance, after a series of dry years, we had big flood events in the Burdekin and the Fitzroy, and we saw a drop, especially in the coastal region, in this water quality indicator. It bounced back pretty quickly in the Fitzroy. There was another year with a high suspended sediment load the following year in the Burdekin, and that's reflected in a continued drop in water quality for 2009 in the dry tropics region. In 2011, we had another big storm event and a large resuspension associated with Cyclone Yassi. The total suspended sediment loads from the rivers were actually lower than in 2008, but we see a fairly deep and sustained dip in this light index, especially in the south. And perhaps one reason for that is that in addition to a high suspended sediments loads and a high resuspension, we had quite a high dissolved in organic nitrogen load in that year, which may mean that in addition to the short-term addition of sediments, we also saw a more sustained phytoplankton response. But that's something that we're taking a closer look at now with some additional analyses of these data. So some of you may be thinking about, well, is satellite data the way to go with this, or should we be using other products such as the Reef's model, which can also tell us an estimate of benthic light each day? Certainly, both products can be used in the same way in creating this index. This slide just shows a comparison of the index calculated from Reef's with the square boxes. Reef's only runs from December 2010 onwards, and the values calculated from the satellite data. They're generally comparable, which is good news that this index could be used to further assess land use change scenarios, although they're not identical. And when I took a closer look at the differences, at least in the mid-shelf regions, the satellite is producing a more reliable day-to-day estimate of benthic light. And it looks like one of the issues in the Reef's estimate is to do with how it handles partial cloud cover. So that's been communicated back to the CSIRO Reef's team, who will be in the next version making some changes to how cloud cover is brought into it. But even as things are, when you look at them over a monthly basis, they provide reasonably comparable values and not identical, but reasonably comparable indexes values. So over the next few weeks, the benthic light data product will become available through eAtlas. For the more technically minded, it will be available both through visualization products, but also as thread served data, so that other people can use it for whatever uses they have for it. We're also working on making it available through Digital Earth, and an advantage of making it available through Digital Earth is that we're hoping it will be able to be an operational product, so it will be updated every day, and that can then be drawn in to future calculations without a big effort. We're hoping that it will be picked up into coming Reef report cards. What else? Oh, it's also already being used, the benthic light product is already being used in collaborations with other NESP projects, and one of the exciting things which has come out recently is that of the environmental data layers available, benthic light seems to be the single best predictor of biodiversity in reef cells. So that's quite exciting too. If you'd like to know more, there's a report from the previous project out on the NESP webpage. I'm just showing the cover of it there. Or ask questions now, or get in touch with me. Thank you, Tracy. Back to you.
Thank you so much, Barbara. I'd like to invite anyone to ask any questions that they might have. So don't forget to unmute yourself first, or alternatively, you can use the chat feature if you don't currently have access to a microphone. But over to you, James.
So Barbara, a really interesting talk. Thanks. And I guess being a seagrass scientist, I could see lots of potential uses for it. I was just wondering, have any of the seagrass groups up in the north, either Catherine, Mike, or others, gone the next step of trying to use the prediction to sort of work out, I guess what I'd love to see is a polygon of the GBR showing areas where benthic light is above that threshold where we would expect seagrass and below?
I have actually produced maps like that, which are in that report that I have up on the screen at the moment.
Okay, I'll tell everyone that you've already saved them a fortune then.
So, and they match up pretty well with the modelled seagrass cover area that Catherine produced using a different methodology a few years ago. So that was encouraging, but we haven't been out to compare it with you know, seagrass biomass.
Yeah, I guess, I mean, in the Rim, I led the RimRep seagrass group. I don't know if you're aware, but I guess out of that was the recommendation, I guess, that across the GBR, really as a first step, we needed to create polygons where we thought seagrass had the potential to live, and then we needed to sample within that. And I know Alex, part of a microsheets group, brought together some polygons using all the data that's been collected on seagrass since the 1970s,
right,
to sort of show where we'd observed it. But I guess we'd like to start with the abiotic approach of where are the physical factors suitable, and then go back to doing some observations within those zones.
Yeah, so I have done a quick version of that, and it didn't seem, it seemed where there had been observations, it seemed to be lining up reasonably.
Okay, that'll be great.
It would be good to do that in more depth.
So they're digital polygons that can be put into GIS package software, is it?
I haven't converted them into polygons at the moment. I just have them as images, but we could convert them to polygons if you like.
Oh, I mean, it's a project, but it is one that I know. I think I was talking to Elaine Marsh last week, and she's recommended in the far north Queensland that something along those lines be done to blend seagrass with dugong mapping. So and this sort of underlying product would be really valuable as I guess it'd reduce overall costs and optimize search image for where we might want to invest our money actually looking. Yeah,
absolutely. And it would, so I've done a rough version, but we'd need a seagrass expert to help us, you know, fine tune it a bit. And yeah.
Oh, thanks a lot. I'll let someone else talk.
Any other questions?
Yes, Andrew Moss here. Hi, Barbara. It's a great talk.
Hi, Andrew.
I was thinking it's a bit sort of along the same lines as James, I suppose. If you can take this a step further to come up with recommendations on what objectives you should set in terms of this indicator, that would be really, you know, really useful, particularly as you can do these calculations across the whole reef rather than just sort of spot measurements of, you know, those in situ recorders or the occasional set your depth, you know. So yeah, have you thought about that?
Only insofar as working out where we should set the thresholds for the A to E scores. You know, in theory, every region could be getting an A because we made sure that the thresholds weren't penalising cells that could never or have never had good light. So depending on how ambitious you wanted to be, you know, you could set a target of A in every region.
Yeah, I know it's a difficult thing to do, but I guess, I mean, in the same way that they've set, you know, chlorophyll sort of based on some of the, perhaps the cake type data, you know, maybe you could do something similar for this.
Yeah, okay. see, there's something in the chat. Can I talk about validation and accuracy from John Cock? So with regards to validation, we have done these validations at the 4 sites where we were able to put loggers out for a sustained period of several months. And this plot gives you pretty much a good idea of the accuracy that we got for daily light estimates at each of those 4 sites. It was slightly worse at Yongala, but still not too, still better than 0.7 R squared. Yongala, of course, has a slightly more variable water quality. We've also had a quick look comparing seagrass light loggers out in the seagrass sites, which tend to be very shallow. Now, one of the limitations of satellite data is that due to all sorts of surface effects with waves and glare and so forth, it tends not to be very reliable in the top 5 metres of the water column. And we're finding in those very shallow seagrass sites, both the satellite algorithm and the Reef's BPAR estimate are tending to overestimate the amount of light getting to the bottom. But I had a really interesting discussion with Ross Jones recently, who I noticed has also joined us. And the error in the light logger estimates is also not been very well characterised because they don't have a uniform detection across the whole photosynthetically active radiation bandwidth. So there's some further work which needs to be done there in estimating the error on the loggers to compare with the error in these 2 data products. It's not going to be perfect, especially in the more optically complex near-shore waters, especially in the very shallow waters. But the fact that it is coming out as one of the best predictors of benthic biodiversity tells us that it's carrying enough information to be useful. So James has asked, does it only work where the satellite can't see the bottom? I don't think so. I think it takes into account bottom reflectance, but I'm not entirely across that swim algorithm which was used in there. So I wish Tess or Lachlan were here to answer that, but I'm not entirely sure.
Barbara, it's Ross Jones. Can you hear me?
Yeah.
How do you deal with cloud cover? Is one question, and have you validated this deep within the turbid reefstone community, sort of inshore of the 18-meter contour? Like, isn't that an essential thing to validate?
Yeah.
In those turbid reef environments.
Yeah. So no, we haven't validated in very turbid water, and that should be done. And we're not dealing with cloud cover very well. There's a gap in the satellite data when there's cloud cover at the time of the satellite overpass. And at the moment, we're simply assuming that on those cloudy days, we have the average light for those months, which obviously is going to be an overestimate of the light on cloudy days. We are hoping to have some improvement on that by taking a closer look at the in situ logger data on cloudy versus clear days, and trying to get sort of rough monthly correction factors that we might be able to apply. But beyond that, there's only so much you can do with ocean colour data during cloudy periods.
Yep, thanks. Thanks.
Thanks.
You can see the question from Rebecca.
Yes, so Rebecca's asked, have you done any sensitivity analysis around how you define the light stress index itself, and if this changes the resulting maps? Yes, in an ad hoc way, and to be honest, there was some sort of fiddling around the edges there in deciding whether to use the 95th percentile or the maximum observed light as the reference, and whether to use that cutoff of 14 or a cutoff of 10 or 11, which would also have been defensible. And we chose the values that we did because when we looked at the actual time series of the index that was calculated for each region, those values gave time series which were both sensitive in that they picked up differences from year to year and from region to region, and accorded with our intuition. You know, we know that light conditions tend to be better offshore in the north, and more variable near shore, and you know, we wanted something that would be reflecting what we know about how the system behaves. So I haven't published a formal sensitivity analysis, but that was done in an ad hoc way in coming to the final values that we used.
Any last questions for Barbara? All right. Well, I just want to sincerely thank you again, Barbara, for your time. Great presentation. Thank you so much for sharing your research with us. With Barbara's permission, I'll be sending around a copy of the recording and the slides to everyone who presented today. So look out for that in your inbox, and I encourage you to get in contact with Barbara with any follow-up questions. Again, if you're interested in hearing in other research related to the Great Barrier Reef, and you'd like us to track that down, or someone who can speak to it, please let us know and we'll do our best. But again, and lastly, thank you to everyone, and thank you to Barbara.
Thank you, Tracy.
Enjoy the rest of your day.
Thanks, everyone.
Thanks, Barbara. It's great.
Thank you, Barbara.
Hey, thanks, Barbara. I actually had just a question.
Oh, my apologies.
Sorry. I just had a couple of either comment or questions, but so the overestimation well, this is kind of known and has previously been also attributed to the effect of bottom reflectance and potentially the type of substrate and shape orientation of distinct type of reefs.
Mm-hmm.
Have you looked at these to look at the effect of that on this benthic power?
Not yet, no. But I'd love to have a longer conversation about that, Benny.
Yeah, and on the other hand, I was just kind of wondering whether there's any perspective into looking at not only the total light, so total power, total spectrum, but the difference in the spectra. So because I'm assuming that different prevalence of spectra will influence different type of corals or seagrass species.
Yes, so as soon as we've got this water quality index published, the next analysis that we'll be doing is looking at how the spectrally resolved KD varied in different events, because I'm really interested in looking at, for instance, whether some storm events tend to be sediments and others tend to be having more of a phytoplankton effect, and because that would, you know, we've previously found that the year-to-year variations in river loads are strongly correlated with changes in photic depth. But the degree to which those changes in photic depth, even, you know, up in the mid-shelf, are due to fine sediments being carried out a long way, or the degree to which they're due to increased phytoplankton productivity, has really big implications for land management, whether it should focus mostly on sediment control or whether nutrient control is also important, and whether that is different in different NRM regions. So that's one of the reasons we are following up that spectral breakdown in a bit more detail, but we haven't got that analysis on yet.
Yeah, okay, cool. Cool, thanks.
Thanks. Okay, thanks again, Tracy.
No worries. All right, well, thanks everyone. Enjoy your day.
Great,
Bye.
thanks.